So you all are able to see my screen.
Yes, sir.
Okay, thank you. So in the last class, we somehow deviated a little bit from the supervised learning in order to get a flavor of the unsupervised setting. And in particular, we discussed clustering, where we discussed different kinds of clustering approaches such as DB-scan, uh, k-means clustering, hierarchical clustering, agglomeratives, and all. However, if we again come back to the supervised learning setting, because the most of the course is in the supervised learning primarily of the reason that in day-to-day lives the problems that you encounter often has a label, and therefore the most of the problems that we solve using machine learning mostly comprises of certain data sets which have also the classes with along with the data. So unsupervised learning is relatively restricted with respect to supervised learning. So we will focus more on supervised learning. And at the end of the course, we will also see the other kinds of learning, for example, reinforcement learning and all. So if we now look forward with our supervised learning setting, so we have seen that how we can get a good learner or how we can develop a good learner using the data sets or the training sets in our hand. However, just consider this scenario that a particular learner is not always the best one, because we do not foresee the test data, because out of sample data we do not have in our hand. So we cannot foresee that a particular learner with only restricted with the training data set can do well in every scenario. Rather, there is a concept that people also tried in machine learning, and as I always keep on telling, that machine learning is all about experiments and it's backed up with statistics and mathematics. So what people have tried, let's say I develop a combination of learners to reason about certain data. For example, let's say I have certain kind of something called weak learners, which means that suppose this is my error, as if we say my error ranges from 0 to 1, and a learner, so if it is this is 0.5, so your learning algorithm should be on the this side, because 0.5 means whatever be the data, you flip a coin and declare its class. So we are saying that two class classification problems. In two class classification, obviously your error boundary should be this. So you are lucky if you get an error like here close to 0. Your learner is lucky, because as you can see, ultimately our aim is that in sample error will track the out of sample error. So the less the in sample error, the less will be the out of sample error as per our inductive learning basis. Now what if I have a weak learner which stands here in the error bar? So suppose this is my error bar. The weak learner stands here. It is not as great as one good learner, but I have a weak learner which whose error rate is less than 0.5. So I have weak learner whose error rate is less than 0.5, but it's high. It's a high error, less than 0.5. And what if I have such kind of a weak learner, many of them, L1, L2, L3, and so on. Now, when I say I have multiple learner, therefore the concept of multiple learner, when I say I have multiple learners, so obviously I am saying that these learner, number one, be can be produced by different algorithms. For example, you can use support vector machines to produce a learner. You can use perceptron learning algorithm to produce a linear learner. You can use any other decision tree algorithm to produce a learner. So those are different kind of algorithms. Support vector machines you are using, perceptron learning algorithm you are using, decision tree learning algorithms you are using, concept learning you are using, and all that. Multiple learners can also be produced by different hyperparameters of the same algorithm. For example, as you know that suppose I am doing only perceptron learning algorithm. Now you can understand that there are different weights that I have to get to learn from the perceptron learning algorithm in order to have it. Now, if you are using perceptron learning algorithm, you can have your line this way or this way, unless and until it separates plus points from the minus points, both are fine. If you are not going into support vector machines. Similarly, in decision tree learning, if you use a different entropy instead of an entropy based measure, if you use a different kind of index like Gini index, your decision tree could be different. Therefore, it means the attribute that you start off with or choose can be different and produce a different decision tree. So the hyperparameters could be different and could produce a different learner. The third one could be you could be using a different training sets. So for example, this is a very vital point people have explored. For example, you are given a training set D. What you do from this training set D, you produce a set of different training set. And each of this training set you use to train your model and produce a different outcome. And you can easily understand that if my training set is different, since I am classifying, obviously my final outcome will be different because it is too much dependent on what is the training data given to me. And the fourth one, which can also be thought about different algorithmic perspective, is that you can have a different representation at all. So by representation means whether I use linear model or whether I use neural network, which is not a linear threshold, but kind of a logistical threshold. So it's a representation wise different of a layer. Or maybe the case that whether you are using probabilistic based classifier kind of a thing, where you only can say not a class +1 or -1, you assign a probability in the output, right? So depending on that, whether you use this kind of a model or a strict this one or perceptron or maybe a probability, so the representations how you invoke the outcome or how you learn and produce your outcome may be different. So there may be many ways in which you can produce different learner from looking into the same machine learning problem. However, the only thing that needs to be guaranteed is the fact that if so each of the when you produce a different one, so everyone will have a certain error rate epsilon. I'm not saying it is just less than 0.5, but if it is just less than 0.5, not too good, then we call it as a weak learner. But the goal is that I will try to produce multiple learners. That's the fine. That's the goal. Now, that's the goal number one. Now try to first pictorially understand that what we will try to achieve by this multiple learner. Suppose I have this as my data set. Now suppose I have learner one which produces error here. So this is the learner one hypothesis. Suppose it is H1. And suppose this is epsilon, I mean the error one, those data points where H1 produces a mistake in the classification. There may be some other one can produce it here. 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 Now see, when I say so, they came up with an hypothesis for a different learning algorithm. So L2 produces this one, H2. L3 produces this H3. L4 produces this H4. L5 produces this H5. Now question number one is that if they are independent and we can take a vote between them, then see almost the error produced by any of them, since they are different, so I am reducing my in-sample error. Did you get this philosophy? If the errors are independent, or let's say if the hypothesis produced is independent, produces independent outcome, that means it will produce independent error sets. So if I take a majority, suppose there are three hypotheses, if two of them doesn't produce error, so here in this case, only hypothesis H1 produces error. Other hypothesis is good in this place. So the role of ensembling, which we call as ensemble learning, is to combine multiple, weak, I am putting it into bracket, ultimately multiple learners. Now, you might argue that this is not the this is a pathological scenario. This is not always the case. So eventually, always the case will be kind of this one, right? Because it would be the case that I produce H1, H2, and H3, and they produces error in an overlapping set of data points. So your bad regions are this much. If you can minimize this common region where they produces error. So what happens in this common region? See, in this common region, either two or three of them produces error together. So the majority of the voting will say that these points are misclassified. So what I will take when I ensemble, when I combine, I will take a majority of the outcomes. So with this, you can immediately think that when I combine, my second goal not only is to get the multiple learners, but to get multiple learners, how much independent way we can get it, right? Independent in a sense, if a learner Li produce an outcome Di, that means outcome Di is +1 or -1. So these DIs will be independent. The way that the learner produces an outcome should be independent of the other. And the more independent it is, the more better it looks in terms of my ensembling. Okay, intuition wise, where we want to land up is clear. Any questions here?
So this independence thing, can you please?
So what I'm saying is that, see, so let us take an example of a different training set. Okay, so suppose someone has been trained with a different training set than other. Then obviously one hypothesis will be different than other, maybe in terms of the hyperparameter values or maybe in terms of the representation, isn't it?
Yes,
Say
sir.
decision tree. If I give you different sets of these training data, then two different decision trees may be produced,
Yes,
right?
sir.
Now the
Yes.
question is that if that outcome, let's say three I have produced, if the outcome are different, that means those three trees does not make error in a single data point together. So it means that if I take a majority of the class, when I combine them, when I combine the decisions, so what I will do, suppose I have three decision trees, let's say decision tree T1, decision tree T2, decision tree T3. I get a new point, X new. I will put it here, I will put it here, I will put it here. Suppose this gives +1, this gives -1, this gives +1. Then I will say X new, the level of X new is +1 because of the majority. So this, if they are independent, this will always succeed because the position where T1 produces error, T2 and T3 will not produce error. The position where T2 produce error, T1 and T3 will not produce error. See this left diagram. So this is the best case if we can get, right?
Yes, sir.
That's what I mean, that when we talk about ensembling learners, if the learners are as much as independent they are, my decision would be that much robust. So it is not the case that we get multiple learners. It is one of the problems, but also the major problem in ensembling is that getting the learners to be independent, right? So let us move on. So this quest, let us first see that what impact can we make it. So let us again go back to our concept of bias and variance. Let me draw a diagram. So what is bias? So suppose this is your hypothesis that you allow, and this is your target function, and you suppose get something like this one as your average hypothesis, with this the distance. You remember, right? The bias and variance, this is your average hypothesis. With that, your function difference is your bias. And with all the hypotheses, what you will get finally, what you will get as your final hypothesis with the average is your variance, right? So the more the bias, less the variance is, because they have a sum to be of the fixed thing. We have all done it, right? So the main point to note here is that bias is the fact that if your set of hypotheses is much more expressive, then it is more likely that it will contain very nearer f inside it. But if it is much more expressive, the problem would be to find the nearest f among a ocean of hypotheses that we have. So it is not only the case your hypothesis is there, your target function is there inside your hypothesis set, but it is also the case you have to find it. So the proximity of target function with respect to the hypothesis set is my bias, and the proximity of what I find it to the best possible hypothesis in this set is the variance. Agreed? Remember?
Yes, sir.
So now the case is that we will see this ensembling. What it will do, since it works on a fragmented piece of different weak learners. So see, weak learners means what? Weak learners means, suppose I get a weak learner, it means that I am far away from I mean, either I am getting a sacrifice in this variance, or I am getting a sacrifice in this bias. So this set of weak learners combinations means that I want to get a little bit low bias as well as little low variance as possible. That's what my case is, because either weak learner will be your model is restricted, so your hypothesis set is lesser. That means you have low variance in that case, or your weak learner could be that your target function is also nearer, your bias is very low. So in a whole, when you combine all this, you can reduce your bias and variance together. Theoretically, why such thing happens? Let us try to take some example and then go theoretically. Suppose we assume n independent learners. Independent thing is very important. Later we will see how to make it. Now in that case, suppose you have n independent learners, and let's say that each produce an error 0.3, which means that your accuracy is 0.7. So if all the n independent learner give same output, the probability of, I mean, the probability, if we take a majority of them, suppose there are n1 plus n2 equal to n, and n1 is greater than n2. So whenever I have this kind of a thing, so you know that the binomial theorem comes into our rescue, where I say the binomial nr and a probability p is ncr p to the power r 1 minus p to the power r. Now, what will be the error rate here? Because n2 is the less number of thing and n1 is my majority. So suppose it will produce class what is given by class n1. So the probability of producing to class of n1 is given as 1.
Sir,
Yes.
sir, it should be 1 minus p to the power n minus r.
Oh yeah, 1 minus p to the power n minus r. Correct. This is n minus r. Yes. So this will be probability of this according to our case with 0.7 accuracy, right? Because n1 is the majority, so I can say that the probability of this class is n2 if I produce in whatsoever way, that is in nc n2 number of ways, the accuracy of is p to the power r, that is p to the power n2, and 1 minus p to the power, the rest is my error. So that cannot happen always, because I am classifying it in n1 is the majority, so 1 minus of that will be my probability. So therefore, what we do essentially is we take odd number of learners in terms of majority voting. We take odd number of learners. If they are independent, then we can use such kind of a theorem to prove that, I mean, to ensemble them finally. Sometimes instead of majority, we also, so the thing that I was trying to first declare is combine part. How do I combine the learners? So this is one way of combining where we get majority to be class 1 or class 2. Later, I will also tackle independence, and I will also tackle why the bias and variance both can be pushed lower. So when I say combine, so one way is that I can take a majority. The other way is that instead of taking a simple majority, which is unweighted, as I have shown in the previous example, we can also take weighted majority. And this weighted, by this weight can also be proportional to accuracy. It could also be proportional to 1 by variance, whose variance is high, I just give him less weight. So when we combine the output, and finally get the output, what we do, for all the learners, let's say I have k number of learners, so I just have a weighted sum of each of the individual outputs. So these are the outputs from Li, the learner Li. Here, the only thing we need to consider that each Wi is greater than equal to 0, and the sum of over all Iwi will be 1, so that to get it normalized, nothing else. So majority is one way we can do it, but we can also do it using a weighted majority way. If we allow this one, you can see it's a weighted majority, because the more the weight, the voting power is more. If all the weights are the same, then it's just an average, because if all the weights are same, if there are k number of weights, so you can see each weight is 1 by k. It is sum over this by k. So it's an average. Now, when we do this, the good thing that happens is, if the output DJ from all of the independent learners are really independent, then look at the variance. What happens? What will happen to the variance of y? The variance of y will be nothing but variance of sum over j 1 by n dj, because all of the learners are independent. So the cross variance terms, the covariance terms will disappear, which will become 1 by n square into n into variance of dj, which will become variance of dj by n. So what do we gain here is this factor. So therefore, you can see that though if I also allow same hypothesis set, for example, I am allowing it to be a linear model. So hypothesis sets are same, but I train them on a different data set, or maybe just do a different parameter, hyperparameter, to come up with the final solution with different learner. However, after ensembling, you can, so the bias will be the same, because I am looking for the same hypothesis set, but my variance decreases. Did you get the point? So let me repeat what I covered till now. Two things. We will try to combine learners to get a better learner. When we say we will try to combine learners, so individual learner, we will not try to make it best. So weak learner will also do for us. Most important criteria is independence. How we will achieve it, we have not declared yet. However, if we can achieve independent learners, which may be weak in itself, we can combine them using majority in case of two classification problems. Majority can be weighted or unweighted. However, the weight should be normalized. And in case of unweighted, it is just the average of whatever be the learner that you take. Now, the advantage of such kind of ensembling is the fact that suppose I only allow you linear models. So when I allow you linear models, that means your hypothesis set is now fixed. And in linear models, you have to just make sure your weights are. So let me not confuse with this one. Let's say my weight should be is the parameter that I need to learn depending on the inputs or the test points. Now suppose if I try to learn using different set of test points and produce a different learner.
Sir,
Yes.
Sir, I didn't understand this formula. Probability of class N1 equal to 1 minus P binomial distribution of N, N2, 0.7.
Okay. Suppose you have 3 points, okay, with an error 0.3, right? 3 learners with an error 0.3. Agreed?
Yes, sir.
So accuracy is 0.7, right? When
Yes,
you will produce wrong answers, so when you will produce wrong answer, when your two classes will be differing, right?
yes, sir.
You will produce wrong answer. How these two classes can differ? 3C2, 0.7 square, 1 minus
Yes, sir.
0.7 not square. I mean, one classes is correct. So 0.7 to the power 1. And two classes are wrong. This. Agreed?
Yes, sir.
So this is how when you can get wrong. Yes or no?
Yes, sir.
When I can get right is this one.
Yes, sir.
So see now the formula. This N2 is the lower one, 2. N2 is for the wrong cases.
Yes, sir.
So this formula is this, isn't it? 1 minus of this.
Yes, sir. Got it.
Okay. So where we are is that when we combine in the, let's say, linear model. So now in case our bias will be the same because we are using the same hypothesis. Now see how the variance decreases because of the fact that each, let's say, from different data point, I just train and make my linear answers L1 to Lk. Now, if they are independent, so that's a very strong assumption, but if they are independent, each of them, then my variance is this. So instead of using only one learner, my variance will significantly decrease depending on the number of learners that I use. Here I assume n such learners. So in other words, if to make everything to be in the same notation wise, instead of n, I was just talking about k number of learners I will do. So let's take it k. So you can see with respect to the number of learners we ensemble, we can reduce both bias as well as variance if we ensemble, right? So that's our motto, where to achieve. Now, there are difficulty in ensembling in some of the cases. Suppose, for example, in Bayesian learning, what we do, we try to predict not only the output class, but a probability that the output class is I, given a data point X, we want to predict it. And according to that, suppose we train this Bayesian classifier using different data sets and produce a different sets of model M1 to MK. Now, this will be a weighted sum of probability of Ci given this point and Mj into probability of Mj, which is our prior. And this will be for all Mjs. And obviously you can make it weighted or unweighted. I am just having it some Wi or W. Yeah, for Ci it's Wi. Now the question is that, see, the difficulty here in applying ensemble is, number one, in case of Bayesian learning, you need to know the prior probability of all these models, which is not at all easy, because it's a prior probability how your model fares, the probability of this model with respect to your data point, that is your prior, the data points that you cannot see even. The other thing is the joint distribution of this is also a very computationally very heavy, because for all classes, for all X and for all different models you produce, you need to have this table, get a sum over it, then you get this probability. So after you get this probability for a new output Y, how do you predict? As you know that whichever class has the maximum probability out of all the classes, let's say Cj belongs to C, I do it that I produce a hypothesis H Bayesian with respect to Bayesian classifier, then I do probability of Cj given Hi into probability of the test points, test examples given Hi into probability of Hi. This is how we do in Bayesian learning, because we only have the test points and we, depending on that with respect to hypothesis, we just try to compute it, do that. But I want to just mention the challenges here. The challenges here is with respect to the prior that we need, because now we are ensembling. So in case of Bayesian learning, it is not very straightforward to ensemble. So what people do, just to make you complete, I am doing it, we will not cover it. People do a Bayesian model average, which is optimal and which uses Monte Carlo simulation kind of a thing to get out these values easily, nothing else. So it is not, so to show you this point is that it is not always easy to directly apply ensemble, but there are models like linear models and decision tree models where ensemble is randomly, we can use it very efficiently and we can randomize the data sets very well and can do that very efficiently. Now, we are always talking about this independent learners. So let us take a dive on this independent learner issues. So the main stuck bottleneck is the independence issue. So suppose the outputs are not independent, they are correlated. So if I again write the previous formula where they are independent, I get var y equal to var dj by k, right? So this was our formula here. So in case of they are independent. So if not they are independent, what will happen to this formula is as follows. So when you do a variance, so that means variance of 1 by k. I mean, there is a summation before. So summation of 1 by k j for all j. When you do this, why I can, with independence notion, why I can reach here? Because the covariance or the cross terms between dj and all di is cancelled. That's why. If they are not independent, if they are correlated, then the same formula would be this was what we got earlier, because this was with this sum of k number of learners, the k comes in here and cancels out 1k here, so I got this one. But due to covariance factor now, or the correlation, I will get cross covariances with respect to these two terms. Now see, still there is an improvement as far as the independence factor we can do. Still there are a lot of improvements that we can make. See, because it's this term which will play spoil sport and try to increase my variance factor, which was, and this term is already this k divided by k. So it is just like this one, this term. Due to covariance, it will try to improve it. But if you have a particular di which is independent than dj, there are k learners. So any one learner is independent of the other will significantly reduce this to 0, and one of the terms will cancel. So as you can understand that even if not all of them are independent, if some of them are independent also, we get a reduction. So it's a good thing to ensemble, first of all. So independence without independence assumption. So this is without independence assumption. We will get this thing, which is not bad because there are scope to improve here. At least some of them may be independent and we could do it. Or maybe there are very less dependency. So these terms are really less and we could make progress. So hence, instead of finding ensembling and the way to ensemble, now the major question that we try to answer, how to make or produce independent learners. So let us try to see that. Is there any questions till this point? Yeah, please.
So how did we get this second equation in variance of y?
Oh, this one, see, when you try to do variance of this sum, you try to push it inside, as we did in the previous this equation. We try to push it inside, and this is k into this, because the covariance is cross terms cancelled. Right? What is variance? What is variance? You just try statistically with this, with the formula, you will get exactly this particular thing. So I mean, if you compute from the first principle, you will essentially get this. But if you know the formulation, so it is nothing but pushing it inside. So pushing it inside means variance of this k number of that. So, and since there are k square number of cross terms, so it has to be divided by k square, and k square cancels. Now here the cross terms doesn't cancel because they are not independent anymore. So I have this covariance term. Okay. Just try to follow what is the equation of variance. What is var of x? You know expectation of x, right? What is var of x? Just try to figure out and just try to solve it with respect to this combination of this. Okay, what is var of x? You try to figure out from statistics. You will yourself do it. That's why I'm not doing. What is var of x1 plus x2? Then you apply this to this k number of summations and just go on doing it. You will find. Okay, so I'm not just giving more time to expand on this one. But the takeaway lesson is that if you have independence, you only have this term. If you have non-independence assumptions, this term is actually somewhat you need to reduce. So you need to make as much as independent the learner are. Therefore, our main question the main bottleneck that we are facing is that how to produce independent learners, and that's the whole essence of ensemble learning, to produce independent learners.
Di, DJ are data points.
DJ is the outcome from the model J. So Y is the outcome of your ensemble.
Okay. Okay.
So to get into this challenge, so one of the way that people try to follow is that instead from a data set, I will try to produce different data sets, D1, D2, D3, and let's say M number of data sets I will try to produce. What is the benefit of that? Now, if I produce those data sets, from there, I can obviously produce different learners, though it is the same. Let's say it's a decision tree. I can produce H1, I can produce H2, I can produce H3, and I can produce HM. Then finally, I just want to combine all of them together and finally try to produce with ensemble the final H, maybe it majority or not. Now, how this could be made is the one of the challenges, because if this could be made in a very good way, then our this hypothesis or the learners that I find out. So remember, one hypothesis is one learner, because hypothesis is the outcome, right? I mean, this is L1. L1 means it's a hypothesis. L2 means it's another hypothesis. LM means it's another hypothesis. So what people do, and which is the most familiar concept in terms of doing it, is called bagging. That is producing or bagging different data points, putting into different baskets and producing different data sets. So how people do it, let us try to understand first. Suppose I have, this is my total data point. It has 1, 2, 3 up to n. So what I will do, I will try to produce from here my data sets D1, D2 up to Dm. Now what I will do, I will take randomly from this with a replacement. Take randomly data from this with a replacement. What does this will do? That when you take randomly data from this with a replacement, that it may be the case that you have 1, 2, 1, 2. It may be the case you have 1, 3, 3, 4, 2, 3, 5, 6. So, however, in practice, it has been shown that usually you will get 60% of different values here, and there will be 40% around repetitions you can find here. But you can see the probability wise, if I try to compute, suppose a particular number each has equal probability of randomly picking up. So a number has a probability to pick up in is 1 by n, right? So in a basket, a number I can pick up a particular number is probability 1 by n, and since I replace, it will always be 1 by n. I can pick up that number. So what is that 1 minus 1 by n? I do not pick up that number. I do not pick up that number in any of the basket is this. Therefore, I pick up a particular number in one of the basket is this probability. Right? Yes or no?
Yes, sir.
Can you
Therefore,
explain?
okay, go back. If a number is randomly taken from the overall basket of n numbers and all numbers are identically independent, I can pick up any number. So each number has probability of picking up is 1 by n. Agreed?
Yes.
If I do it with replacement, every time I pick up a number, the probability remains same 1 by n. If it is replaced,
Yes.
therefore, a number is not picked up, probability is this.
Yes.
A number is not picked up in any of the draws. Let's say if there are m draws, is this.
Yes.
A number is picked up in any one of them, is this.
Okay.
Okay. So a number is not picked up by any one of them. So a number is picked up by any one of them is this. There are m of them. You can see that a number is not picked up by any one of them is very less. I mean, it will not be the case almost. So I am just showing you how to calculate the probability. In this way, if you calculate in most practical scenarios, suppose you have 1,000 data points and all, you will see almost 63% of the data are not repeating, 40% may be repeating. So that's the success of bagging. So that means I can have a very independent data set produced through this kind of an approach. Almost very independent. So almost very independent in a sense, if you look at this, I can reduce this covariance very less if I produce a new model from that data sets. Okay. So this is called, this is the overall procedure is bagging, and particularly this process that I mentioned, sample with replacement, is called bootstrapping. And there is a nice history of bootstrapping. See, bootstrapping name comes from, I mean, it's just when there is no hope. And so the story goes like this, that somebody was going in a mountain climbing, and he was stuck in a ice kind of an avalanche, and there is no hope for him to be alive. So he can, how he can pull himself up, he just pull the bootstraps and lift himself up. I mean, that's a very funny story, how one person can lift himself up by strapping from the bootstrap. But from there the name comes, that where there is no hope of doing good, bootstrapping comes into picture. That is a ray of hope. So you split this training sets into different cluster of training sets, and essentially the number of these different training sets as you can make is higher, the better is your ensemble, because now you are producing many things and you can ensemble it in a proper way. So one of the algorithms that is most successful in machine learning, and everywhere it is used, even in this $1 million prize of Netflix competition, is random forest as well, which is ensembling of data trees using this bootstrapping method. Decision trees using this bootstrapping. So what is very good about random forest, or why people love random forest so much, is that not only with respect to data, bootstrap data, it tries to classify, but it also tries to incorporate certain randomizations in the decision tree being formed. See, this is the point where we are putting here. This is the point where we are impacting here through bagging or bootstrapping methodology, that we are creating new data sets. But the same random tree, entropy based or something, or Gini based, we are trying and getting same decision tree we are getting with different forests. So the decision tree are different because you have different data sets to start with. However, random forest also do that, your model also they tune it. What they do is that suppose you have this set of attributes A1 to AL, let's say. Now, when they create the data points, and when they create the decision trees from a data point, they take a subset of the attributes. And then based on that, they try to figure out which one has the highest entropy, split it, next highest entropy, split it, and so on. Okay, so it uses bootstrapping to create all the different data sets, D1 to DM, and a very large of them. It creates a randomized attribute set to start with building each of the data types. So D1 will be used over this part of the attribute produces this H1. D2 will be used maybe this part of the attribute it takes produces H2 disease entry. And secondly, what it does, it goes exactly till the end until and unless it can split every attribute. Even if there are two attributes, it split. If unless and until there are two attributes, both are of same class, it's go on splitting like this at the end. So what it does is that you see it overfits. You can see each of these disease entry is also overfitting. If you do not prune and go till the end, that means what? Every attribute exactly you are trying to split. So suppose you have this kind of a thing in a decision tree setup and you go till the end. That means what you are doing? You are doing this, you are doing this. Suppose there is some minus here, then you are doing this and like that. So you go exactly till the end of the decision tree by splitting all the points. So it is overfitting. Now, overfitting means it's not a good learner, right? Overfitting means it's not a good learner, it's a weak learner, obviously. And it only tries to fit these data points very drastically with respect to the data sets that I am given. In the second iteration, the data sets is different. Your attribute space is different. So maybe this x1 and x2 are no longer taken in a different attribute dimension you are trying to do it. So that's why this is very much successful because it does a two-step randomization. And most interestingly, decision tree was a gone concept because people could not scale beyond a certain point and people could not, apart from the reasoning aspect of decision tree, it is no longer being used. However, the person who has invented this bagging bootstrapping principle, he showed, or rather she showed, that this is a very nice method of ensembling and again it gains attention. That's the beauty of random forest. Any questions in this? How can we try to make learners independent from the random forest perspective? And it is a forest because we ensemble decision trees together. It's a tree, set of trees, so it's a forest.
Sir, I have a question. What is the difference between bagging and bootstrapping?
No, bagging is the procedure of bagging things into data the cluster of data points. Bootstrapping is one of the algorithms to do that. The algorithms that I mentioned, I mean, take sample and replace it. It's a bootstrapping algorithm.
Okay.
Bagging is the overall methodology. That bagging is the methodology to create set of data sets. Now, how do you do it? One methodology is bootstrapping. There are other methodologies as well, but bootstrapping is the most popular methodology to do it. And in random forest, we first use bootstrap to create different data points or data sets, and then use this kind of randomized attribute choice and the decision tree overfitting till the end and ensemble it. That's the random forest. Okay. So you can also see that, see, stratified, you know that stratified sampling one day we discussed is also a kind of a bagging technique. What we do, we have what this data point says. Data point says x1 plus, x2 plus, x3 minus, x4 plus. This will be my combinations of data points that will be given to me, right? So when I create different clusters, what does strata do? I just put the plus things together, x1 plus, x2 plus, x4 plus, and the minus thing together, x1 minus, x3 minus, maybe x7 minus, x11 minus. So now from these two sets, I randomly choose and build my stratas. Remember stratified sampling? Yes or no?
Yes, sir.
So I randomly choose from each of these sets and create my stratas. So this is also a kind of a bagging, where in this way I produce different data sets. So that's why when one of your friend asked that bootstrapping is a method. So this is a method 1. The stratified sampling is a method 2 of producing different data sets. But random forest is an algorithm to use ensembling method over this bagging procedure. So the other way, the final way that I will discuss before closing is called a different approach. So here we just take a sample, replace it, or maybe make stratas, take samples with similar number of pluses and similar number of minuses and put into it. So these are ways to do it. And assuming that the probability of each of the data points to be taken are same. In the bagging, that's the assumption. There is another method which is called boosting. So gradually, when people were trying to solve this Netflix competition, they first invented this bagging random forest bootstrapping. Then they invented the boosting is much more efficient than that as well. So what does boosting do in the same thing? Let us try to see that. Suppose I have a data set of n points. Initially, when I create my baskets D1 up to say Dm, each of the data point has the probability 1 by n to pick up. That is, for each of the data points, I give same weights. Okay, so it's unweighted or the same weight, I would say, to pick up each of the points. Now, when I pick up each of the points and create one data set, let's say the first data set I created by picking up a set of points from here with same probability. I run my learning algorithm and produced a hypothesis. That hypothesis that I produce, I will try to see which of the data points it is not clustering correctly, not classifying correctly. Suppose this it classifies correct, this is classifies correct, this it classified wrong, this it is wrong, something else is correct, here it is correct, somewhere here is wrong, this may be correct. Now what I do is that, see, now try to think about the concept that this is the classifier that I got choosing these points, which is not performing well in these points. Maybe somewhere here it's also not performing well. So therefore, in the space of errors, these points form somewhere here where it is not performing well, right? So I need to make an independent learner at the next iteration. So I will try to choose these points into my data sets with even higher bias. Earlier, since it's the same weight in the first iteration, nobody has a preference to be chosen. Now, since these are the points where my first hypothesis is making an error, I will try to choose those points intentionally with a more preference while creating my second dataset D2. So what I will do, I will try to increase the weights of these points where it misclassified by the first. However, you know the summation of the weights is 1. So I need to decrease all other points weights where the first hypothesis classified correctly. So then what will happen? The probability of misclassified data points has increased. Probability of good classified data points have decreased. In the second draw, when I create D2, there are tendency to have these cross points more than the tendency to have this good classified point. So with that, I again run the learning algorithm to produce H2. I will see which are the points where H1 and H2 both misclassifies. Reduce other points probability, misclassified probability further increase. Take a new sample D3. Produce L3, sorry, produce H3 by L3. Go on doing that. So this, what it will essentially do, it will try to produce hypotheses which are very less overlapping. Even people experimentally has shown, I mean, even with respect to bagging also, this produces very nice hypotheses or independent learners, so-called. So this is the most popular ensemble technique used in machine learning, which is called AdaBoost. And what I will do, the next class fully I will devote for this AdaBoost, which is adaptive boosting. That is, it's an adaptation of the probability of data taking in boosting. Okay, so in summary, we have weak algo, and we want to give strong learner from that weak algorithm. So the way we proceed from the weak algorithm, we produce different weak learners. We ensemble them to produce a strong learner. What we have seen in the process is that the variance goes low. The bias stays as it is, because if I get it from the same hypothesis set. And these learners, the main challenge of this learner is independence. So to get into independent factor, what we have done, either we tried to do bagging, which we have seen, bootstrap, sample, stratified. And in the next class, what we will mostly see is the boosting. The philosophy we learned today, that this we will do, but the main method that we will use for boosting is AdaBoost. Okay, so this is how the ensemble, we have to learn the ensemble learning in this philosophical order. Any questions? So this is all for today. Any questions from anyone? So tomorrow's class will be a little theoretical. I will try to show with the independence factor how it is happening, what is the error rate going on, and all that we will try to deduce. And we will use AdaBoost, because you must know AdaBoost if you have done a machine learning course. Somebody asks you, you should tell that I know AdaBoost. Okay, if there are no more questions, so we can stop, I think. Okay.
So
Yes.
it's not a question related to this, but I have come across a classification problem. In there, the multiple ensemblers were used, like random forest were also used, as well as this AdaBoost.
Yes,
So
yes.
is it a good method?
Yes, yes. See, ensemble is your free world, that you can ensemble it in any way. I can ensemble with different algorithms. I can ensemble with different methods, right? So what you are saying is not only ensembling with respect to an algorithm, but also different methods of ensembling.
Yes, sir.
Meta level. Yes, you can use it. People use that.
Okay, sir. Thank you.
Okay.